Okay, so in this last video here of this chapter 8, I just wanted to mention there to use a solver, we must have the form y prime equals f of ty. Okay, so that would be a scalar, but you could have this in vector form as well, or y prime equals f. So that's a vector valued function of t and y. Okay, and so this works for a system as well, right? So example, like y1 prime is equal to y1 minus y2, maybe plus t, and y2 prime is equal to y1 y2 plus cosine of t, something like that. Okay, so this system of differential equations you can plug into Euler's method, for example. The thing is, you have to be sure that when you return your derivative, that it's in vector form, right? So if I were to write this in MATLAB, I would say function, for example, dy is equal to my func ty, and now y is going to have, I can assume that y is going to have more than one value, and my dy is going to be the same size as y. Okay, and so we could even say, well, we should know what our dimension is when we're writing this function. So in this case, for example, right, I would write dy1 is equal to y1 minus y2 plus the t value that's coming out, and then dy2 would be y1 times y2 plus cosine of t. Okay, and that would be the end of your little subroutine. Okay, so now you can call this in any of the ODE algorithms to compute your derivative. Good. So systems are kind of built in. The other way, or the conversion that I wanted to talk about, was just to remind you that back in differential equations we talked about these. How do we convert an nth order dE to first order? Well, for one thing, an nth order differential equation is going to have to become an system of n first order equations. Okay, so just as an example, we might have y triple prime plus y1, not y1, plus y prime equals, say, y double prime plus cosine of t. And I want to convert to a system of first order. Okay, so how do I do that? Well, we bring in new variables. So we're going to let x1 be equal to y, x2 be equal to y prime, that's a comma by the way, and then x3 is going to be y double prime. And so you're always going to have the number of variables equal to one less than the order of your original here. So this is third order. And so here I have three variables that I'm introducing. Okay, and so this is the zeroth derivative. That's why that starts or ends with the second derivative instead of the third. Okay, and then when we write down our differential equations, you need to write them in order. Be sure and write them in order: x1 prime, x2 prime, then x3 prime. And of course, if we just look at our definitions here, x1 prime is y prime, which is x2. x2 prime is y double prime, which is x3. And then x3 prime is y triple prime, And And so just as a side note, right, we can write x3 prime is going to be minus y prime plus y double prime plus cosine of t. And so then this is minus y is x1, y prime is x2 plus x3, and then cosine t just drops down. So this becomes minus x1, x2 plus x3 plus cosine of t. Good. So this is the system of differential equations that corresponds to this third order differential equation. And so if I want to solve the third order differential equation, I would solve this, right? But then remember, when you're in your solution after solving, the original solution is where? The original solution is x1, right? Because that's x1 is equal to y here. Okay? And so you can plug that all into the differential equation solver, and so we can solve all nth order differential equations now using a first order solver. Good. And so that's how it all works. We'll be playing around with some systems of differential equations on Wednesday. We'll have a live session on Wednesday as well, but we'll talk about that more later. Okay, see you on Wednesday.